there's this thing that happens which is called overfitting. So who's heard of overfitting before? Yeah, where did you learn about overfitting? Like, is that in the class? Just like reading the internet? Statistics? Yeah. Okay. So what does overfitting mean? Okay, so let me give you an example. So you know you can go to brokerage houses, right? And they will sell you mutual funds. And what they'll say is they'll say something like, this fund has beat the Lipper average or something like it's beat the market for the past 5 years. That would lead you to believe that the people who start those funds are really smart and they know what they're doing. Here's what they might not be telling you, is what they did was they constructed 100 funds. And they ran those funds for 5 years just behind the scenes. And they picked the 2 that actually did pretty well. Right? And so, if I guarantee you, if everybody in this room went out and we all formed our own mutual fund, one of them would work pretty well over a 5-year period. Now, does that mean that that one person is super smart and is a financial genius? Or does it mean that they got lucky? What do you think? Well, clearly I want you to say they got lucky, right? So, but why is that the case, right? If you sort of extend that example and say, all right, it's not just the 50 people in this room, we're going to get everybody at UMBC, right? Like all 12,000 people on campus are going to start their own fund. Somebody's going to crush it, right? And it might be me, and I'm terrible at that kind of stuff, right? And I would have totally gotten lucky. So how does that play out in machine learning? I just want to say the following, and then like I said, we'll dig into it deeper a little bit later. Imagine I have a data set that has 100 instances in it, and the class label is binary. Oh, I'm sorry, can I modify the example? I just want 20 instances. Class label is binary, and I have 2 binary features, right? So now I've lost my chalk. Don't tell me. Tell me, where is it?
Yeah, I see.
Is it mine?
I noticed like another one.
No, I had no, here it is. Okay, sorry. I had a large, awesome piece of chalk, so. Okay, so think about this. So think about I've got 2 attributes, A1 and A2, and I've got this class label here that can be either 0 or 1, right? Now suppose that using some combination of A1 and A2, I can perfectly predict the class label for 20 different instances. I'd say, I look at that and say, okay, it looks to me like A1 and A2 convey some information about the class label. What if, on the other hand, I had A1, A2 through A1 times 10 to the 12, right? I don't even know what, that's a million, billion, trillion. Is that trillion?
Trillion.
A trillion, so I got a trillion features, right? Do you believe that I got a trillion features here, and let's imagine that they're all completely random. I got to figure that one of them is probably going to perfectly correlate with these 20 instances. This is going to do a really good job. So the problem is that the more features you have, the more likely it is that you could identify what you think is structure, but just as by random chance is allowing you to do well on the prediction. And so we need to take care to avoid those kinds of things. So I just want to introduce that idea that essentially there's this sort of weird thing in machine learning and data mining that says the more times you ask questions of the data, every once in a while the data will come back and go, yep, right? Where it turns out that that yep is just a false relationship. Okay? All right, so file that away. Now, one thing I want to say is that all of this assumes that the data is what? That the data are categorical, right? So what I'm doing is I'm saying, what are all the possible values that attribute can take on? Here we have sort of all the class labels that can be taken on. So we're assuming that the underlying data is categorical. Decision trees, one of their advantages is that they can deal with categorical and real value data. And the standard way of dealing with real value data is to say, suppose I have an attribute and we have a class label, right? And let's suppose we've got attributes that looks like this. So we have this one attribute, 12, 14. Okay, I'm not being very creative. Right? And then here I'm going to give you the class labels. I'll use pluses and minus. Okay. So what we tend to do when we've got real valued attributes is to simply convert them into binary attributes by splitting somewhere in the real range. Now, we could consider any possible value, but it turns out that a very sensible thing is just to consider splitting in between adjacent observed values. Right? So instead of considering all possible real value splits, we'll do something that looks like that. Now, of those splits that I've drawn there, can somebody tell, like, what's the best one? What do you think is the best one? So remember, what I'm going to do is I say, look, I've got these instances. Attribute A takes on value 10, 12, 14, 16, 18, 23, and 30. Right? For the instance for which attribute A had the value 10, it was a positive instance. When it was value 12, it was a positive instance. 14, it was a negative instance. So any idea, like, what's your intuition? 18, what? This one. Is that what you're saying? Right. Why? Only one mistake. Who said that? Good. Yeah. Okay. So what you can imagine doing is essentially doing exactly the same information gain computation. But what I'm going to do is I'll say, suppose I split here, what's the entropy? Right? If I split here, this side is pure, but this side is actually split pretty evenly. Actually, it's 50-50. Right? If I split here, this side is pure, that's a little more pure. That's more pure than it was, right? But the idea is, if I split here, I've got 100% negatives here, and I only make one mistake out of 5, right? So you do exactly the same trick. So under the hood, this should all be happening for you. I will say that the decision tree implementation in scikit-learn, which is the one that we're going to use, is frustrating in a number of ways, but it's what we're going to use, right? So I'm going to give you a little infrastructure to deal with it. Scikit-learn's implementation wants everything to be a real value. It wants the attribute values to be real values. It wants the class labels to be integers, and that's a little bit of a pain, but you know we'll sort of get around it. Okay. Now, what I'd like to do is let's just do a real quick exercise. Okay. Let me pass these things out, and hopefully we have enough examples. This is just a data set. I could project it on the screen, but for some reason I'm not. You just take one and pass it around.